In this lesson, we will learn how radicals are related to rational exponents. Since we already know the meaning of powers like 2 to the power 3, 4 to the power 5, and 12 to the power 0, it becomes natural to define what it means to write expressions like 2 to the power 3 halves and other numbers raised to powers that are no longer integers or that are exponents. Their exponents are rational. So, suppose we want to find the meaning of 2 to the power 3 halves. What we're going to do first is just let this variable x be that number 2 to the power 3 halves, and our goal will be to figure out what is x exactly. Okay, well, since x is 2 to the power 3 halves, notice that x times x would be 2 to the power 3 halves times 2 to the power 3 halves, which, by the product rule, is 2 to the power 6 halves, because if you recall, whenever you have two powers multiplied together with the same base, different exponents, you just add the exponents together. So you end up getting 2 to the power 3 halves plus 3 halves, which is 2 to the power 6 over 2, which can be simplified 2 to the power 3, which is 8. So in other words, basically what we just figured out is that when you square this number x, you get 8. By convention, what we say is that x is the positive square root of 8, so that we can write that 2 to the power 3 halves, which is x, is the square root of 8 in this way here. But notice that we can write what's underneath the radical, which is called the radicand. We could write that as 2 to the power 3, and notice the relationship between this number 2 to the power 3 halves and this expression in radical form here. The 2 in the denominator just becomes the index of the radical, and the 3 in the numerator just becomes the exponent in the radicand. Okay, so a radical expression is any expression that's written using the radical sign, just like this one here. It's called a radical expression. A radical expression has an index, which is some positive integer, and a radicand. This number underneath the radical sign is called the radicand. The way that you read this expression here is you call it the nth root of a. So you call this radical expression the nth root of a. It represents the number whose nth power is a. When n is an even number, a positive number a has two nth roots, one positive and one negative. So for example, if I'm trying to take the square root of 16, notice that you're going to have both positive and negative 4. Okay. But what we're going to say is, from now on, whenever you see the nth root of a and n is an even number, what we're going to say is this expression, we just take the positive nth root only, just by convention. When the index is not shown, it's implied that the index is 2. Okay, so whenever you don't see a number here, you assume that the index is 2. And the radical expression is called a square root. For example, the positive square root of 25, which I can write in this symbol here, represents 5 because 5 squared is 25. If the index is 3, we give the radical expression a special name again, and we call it the cube root. For example, the cube root of negative 8, which we can write like this, with 3 as the index and negative 8 as the radicand. The cube root of negative 8 is negative 2 because negative 2 to the third power is negative 8, since negative 2 to the third power is just negative 2 times negative 2 times negative 2. Okay, you can write a radical as a power by extending the properties of integer exponents. So, for instance, let's say I wanted to write the square root of a as some power of a. We can do it as follows. Notice that the square root of a squared will be a, because that is what the definition of square root is anyway. Also, since I would like to write the square root of a as a power of a to the k, I'm just going to substitute that in here so I can figure out what k has to be in order for this to make sense. Notice that I can simplify this by the power of a product property. Okay, I have a power raised to another power, so what I do is I multiply these two numbers together and keep the same base, and I get a to the power 2k equals a to the power 1, which is the same thing as just a. Since these two have the same exact base, these numbers here, 2k and 1, have to be the exact same thing, and then I just solve for k. K has to be 1/2 in order to make this expression true. So in the end, what I figured out is if I want to write the square root of a radical expression, as a power, as a to some exponent, that exponent has to be 1/2 in order for this to make sense. This result can be generalized to any nth root of a and any nth root of a power a. So this right here is the key to this entire lesson. What you guys just learned is that if I want to take the nth root of a, the radical expression, and write it as a to some exponent, or in other words, as a power to a rational exponent, what I do is I take the index, and the index then becomes the denominator in my power with rational exponent. Similarly here, if I have the nth root of a to some power m, once again n becomes the denominator in my rational exponent, and m becomes the numerator in my rational exponent. Remember to come to class prepared with answers to these reflect questions. Okay, so here are some properties of rational exponents that we can use to simplify expressions that are in radical form in order to rewrite them in rational exponent form. These are things that we already learned from the last lesson, part 1. We already learned that if you have a product of powers like you have here with the same base, then you essentially just add the exponents. That's called the product of powers property. Okay, if you have the same base here, like you have in this case here, raised to two different exponents, you just subtract the exponents as long as a is not equal to 0, because then division by 0 would make no sense. This is called the quotient of powers property. So for example, if I have 5 to the power 4 divided by 5 to the power 2, that would be 5 to the power 4 minus 2, which is 5 squared, or 25. Also, you guys learned the power of a product property. Whenever you have a product here and then the entire product is raised to some power n, essentially what happens is this power n, or the exponent n, gets distributed inside to each factor in my product. So I'd end up having a to the power n times b to the power n as such. Okay, and if I have a power of a quotient, so this is a quotient raised to some power, essentially this n gets distributed to both the numerator and the denominator, and would become this quotient here, as long as b is not equal to 0, once again because division by 0 makes no sense. If you have a power raised to some other power, like you have in this case here, you just multiply these two exponents together, rewrite your base. So I could rewrite this expression here, this expression here, as a to the power m times n. The negative exponent property, if you have a to some power negative n, this just becomes 1 over a to the positive version of this exponent here. So you essentially just you get rid of the negative sign and write this as a quotient, 1 over a to the power n. Once again, a cannot be 0 because division by 0 makes no sense. Okay, so let's show an example how you can use these properties to simplify radical expressions. So let's say we had to rewrite this expression here into a simpler form. Alright, so the first thing I want to do is use the rule that we learned that relates radical expressions to expressions with rational exponents. And what I find is, remember that the power in the radicand, or the exponent in the radicand here, becomes the numerator in my rational exponent, and the root, or the index, becomes the denominator in my rational exponent. So I've rewritten this rational expression, or I'm sorry, this radical expression, as a power with a radical exponent. Notice 6 divided by 3 is just 2, so I can simplify my exponent like this. And using the power of a product property, notice I have a product raised to an entire power. This 2 essentially just gets distributed inside to both factors, and I get x squared times y squared. Looking at another example, let's say I want to simplify this radical expression here. The first thing I might do is rewrite the square root of x, the radical expression square root of x, as an expression that involves rational exponents. So if you remember, the implied index here is 2. the implied index here is 2. So the rule that we learned is that this index becomes the denominator in my rational exponent. So I could write square root of x as x to the power 1/2. And I could write the cube root of x as x to the power 1/3, because once again the index in your radical expression becomes the denominator in your power raised to the rational exponent. Using the product of powers property, I can rewrite this product of powers here. Since they have the same exact base, this would become x to the power 1/2 plus 1/3. Adding up these fractions, I get that this is x to the power 5/6. And then I would rewrite this expression in radical form. Remember, the denominator becomes the index, and the numerator becomes the exponent in the radicand. Another example here. Notice I have a quotient this time. First thing I want to do once again is rewrite this radical expression here as a power raised to a rational exponent. The square root of x I could always write as x to the power 1/2, because once again the implied index here of my radical expression is 2. That becomes my denominator in the rational expression. I could do the exact same thing with the 4th root of x. Here's my index, which is 4. That becomes the denominator in my power raised to a rational exponent. Okay. Using the quotient of powers property, notice that I have x in the numerator, x in the denominator, so I have the same base. Therefore, to simplify this, I can just use the quotient of powers property, rewrite your base, and subtract the numerator minus the denominator, so I get 1/2 minus 1/4 as my new exponent. Subtracting these two fractions here, I get x to the power 1/4, which I can then rewrite as a radical expression. Since my denominator is 4, that becomes the index. The numerator is 1. Of course, we don't write the 1. You could write x to the power 1, which is just x, but we typically don't do that. So this is the simplified version of this expression. Okay, one last example here. Let's say that I have this expression here. Notice that it's a power raised to a rational exponent. Okay, the first thing I might do is use the power of a product property to distribute this exponent here inside to my two factors inside. Okay, and notice I could rewrite 27 as 3 to the power 3, because 3 times 3 times 3 is 27. So I could write 27 as 3 to the power 3rd. Distributing this 2/3 into both my factors, I get 3 to the power 3, and that power is raised to yet another power of 2/3 after distributing inside. X to the power 9, distributing the 2/3 into that factor as well, I get x to the power 9 raised to the power 2/3. Using the power of a power property, because notice I have a power raised to another power, this becomes multiplication. So I have 3 to the power 3 times 2/3. Similarly here, I have x to the power 9 times 2/3, because I have a power raised to another power, so this becomes multiplication here. To simplify, alright, and then simplifying my exponents, I have 3 times 2/3 is 3 squared, and x, or 9 times 2/3 is 6, so I could rewrite this expression this way. Whenever you see something like 3 squared, remember to always evaluate the numerical power, since it's simple to do in this case. It would be 9 to the power, or 9 times x to the power 6. So this is the simplified version of this expression here. Okay, so the question that we aim to answer in this lesson is, how are radicals related to rational exponents? And they're related by these formulas here. Whenever I have a radical expression, like this one here, where my index is n, this n just becomes the denominator in my rational exponent, in my power here. Similarly, if I have the nth root of any number raised to the power m, then the index here once again becomes the denominator in my rational exponent, and the exponent m becomes the numerator in my rational exponent.